here's one question for you. It says a circuit consists of an inductor and a resistor. Choose all of the following statements that are true immediately after the switch is closed at time t equal to 0. The current in the circuit starts at 0 current initially, gradually increases to maximum, becomes equal to maximum immediately. 1 only, 2 only, 3 only, 1 and 2, none of the above. All right, it looks like most of you got the right answer, because what we discussed last time was that in this particular situation, if you close the switch, what happens? As soon as you close the switch, the battery is trying to send a current in which direction? The battery is sending a current in this direction, because the electrons start to move from the lower potential to the higher potential this way. So we say that a current is flowing this way. But as soon as the current starts to flow this way from the battery, this coil, this inductor, sees that there is a change in magnetic flux through it due to this battery current, and it opposes it, right? And since it opposes it according to Faraday's law and Lenz's law, what happens is that the induced current in it opposes the battery current, and so it tries to send a current in the induced current is in this direction as opposed to the battery current, which is in that direction. So I net will be basically the sum of these two, and you can see that they are subtracting, right? And because of that, the net current is not going to be, this is the I net as a function of time. This will actually slowly increase as opposed to gradually increase. In fact, today we are going to derive an expression for how exactly we can find at any given time. I can tell you exactly, you can tell me exactly how much should be the current in this circuit. We can just solve a differential equation and we can figure it out. But conceptually, you can see that the current will not become maximum all of a sudden because the inductor is opposing it, right? Is this making sense? Okay. Let's look at the next question. It says choose one of the following statements that's correct. The larger is the self-inductance of a coil, the more it will oppose an increase in the current through it, the less it will oppose an increase or decrease in current through it, the more it will oppose an increase in current through it. 1 only, 2 only, 3 only, 1 and 3 only, none of the above. Please talk to a person next to you. Your time starts now. All right, the correct answer again here is D. That means the more it will oppose an increase or a decrease in current through it, because, so great, it looks like most of you got the right answer, because if you remember from last time what we said, that the induced EMF in this coil, the induced EMF according to Faraday's law, what is it? Minus N d phi over dt, right? This is what it is, but you can always take N inside this, so we said we can write it as this because N is a constant anyway for these coils. Now if you recall from what we learned last time, we learned that L times I should be equal to N times phi. This is exactly the way the self-inductance was defined. This quantity called self-inductance of a coil or a solenoid or of an inductor, all these things are the same thing. You can call it a coil or an inductor or a solenoid. The self-inductance of this thing was defined this way, that L times this property L times I was equal to N times phi. So instead of N times phi, I can write L times I. So V induced then becomes equal to minus d over dt of L times I instead of N times phi, and L is a constant, so we can pull it out. So you can see that V induced is equal to minus L di over dt. This is the induced EMF, right? Can we find the induced current in the circuit? Yeah. Once you know the induced EMF, induced current will be just this divided by the resistance, wouldn't it? So do you see that it depends upon L? Larger is the L, more is the induced EMF and induced current, right? And that means there is more opposition to increasing the current due to the battery all of a sudden in the circuit. So there is more opposition from the coil, and there's more tendency to maintain a status quo in terms of how much flux is passing through this coil if the self-inductance is more, right? Okay. All right, so let's move on. Here is a question. It says, choose all of the following statements that are correct. Whenever there is a change in the magnetic field in a region, an electric field is induced in the region. An electric field is induced which is due to a conservative force similar to the electric field produced by static charges. An electric field is induced which forms closed loops. There are 5 choices given. Talk to a person next to you. Your time starts now. All right, the correct answer here is again 1 and 3, which is D. And because you can see that in this case, the electric field that is induced does form closed loops, so 3 is correct, and there is an induced electric field, right? Remember, like we could write this thing, the EMF induced as integral E dot dl. But the point is, this electric field is very different from the kind of electric field that are produced by static charges. In those cases, you never saw things looping on themselves like this, because electric field due to static charges are always produced by positive charges, and they always actually end at negative. Here, these things are always forming closed loops. So you can follow an arrow and you can come back all the way to the same point, and also there will be work done in moving a charge through this, unlike the case of electric field that is produced by static charges. In those cases, remember, that is produced by conservative forces, Coulomb force, the force that is given by Coulomb's law. And that in that kind of case, if suppose you move a charge from some point and come back to the same point, is there any work done by that electric field? No. For static charges, the electric field that is produced by Coulomb's law is a conservative force. You know, the Coulomb force is a conservative force. So in that case, there will not be any work done if you move some charge in that field produced by static charges and come back to the same point, because the work done only depends upon initial and final point. Here, the work done actually depends upon the path, the electric field that is produced due to this induced EMF. So remember, this can be written as E induced dot dl. But the point is that E induced actually is not due to a conservative force. This is a very different kind of electric field. You have to keep this in mind. So the work done in this case by this electric field will depend upon the path. It doesn't just depend upon initial and final points. Is that clear? Okay. Okay. All right, let's move on then. Today the first thing that we are going to talk about will be RL circuit, something that we have already done, but this time we are going to do it mathematically. So already I have described to you this situation here, and I've already said that the current doesn't all of a sudden go to its maximum value when you close the switch. Or when you open the switch, suppose the coil gets used to this thing after a long time, suppose you close the switch, yes, initially the coil opposes, and that's why the total current in the circuit, which is going to be a sum of the current due to battery and the induced current. In other words, the battery is trying to push the electrons one way, the coil, this induced EMF, is trying to push the electrons the other way. The net current slowly increases in it, and then it saturates out. It becomes, because the coil gets used to having a current through it. And then, do you know what this thing will be? What will be the maximum current in this circuit? Can anybody tell me what would be the maximum current in this circuit in terms of the battery voltage? Suppose the battery is a 9-volt battery. And let's say the resistance in this circuit is 3 ohms. Can you tell me what would be the maximum current there then in this circuit? Yeah, it will be V divided by R, right? So 3 exactly. Because of the fact that after a long time, this coil becomes useless, right? It doesn't oppose things anymore. It gets used to what you have done. So you've closed the switch. Initially it opposes while you are closing the switch, but after a while it gets used to it, and in that case the current will become constant, and I max will become V battery divided by R. So in this case 9 divided by 3, which is 3 amperes, right? But let's try to see the whole thing in a nice mathematical way where all of this will just drop out of the math, all right? So let's try, but is conceptually everybody understanding what we are talking about and why this coil opposes? It's because of Faraday's law, right? All right, so now let's try to think about this problem mathematically, and all we are going to do is we are going to make use of Kirchhoff's rules. Remember we use Kirchhoff's rule. So if you go through a loop, go from here to here, here to here, here to here, come back, all of the voltages should add up to 0, right? So let's try to go over, start from some point. Let's say we go from here, A, B, C, D. So we are talking about RL circuit. So using Kirchhoff's rule, for voltage, and let's use it for voltage, then what we see is if we go through a loop, the sum of voltages over a loop adds up to 0. This sigma means sum. So sum over a loop is 0. So let's go from somewhere, let's say, by the way, V battery is always going to win out in the end, right? So in the end, your I net is going to be in this direction if you have a battery. This is going to be your I. This is going to be your I. This is going to be your I. But let's say that we have just closed the switch, okay? So this time we are going to talk about the case case 1 where we close the switch, just close the switch. So in the case where we just closed the switch was initially open, then we closed it, the battery is trying to send current this way, this coil is opposing according to Faraday's law like this, and it's trying to send its I induced in the opposite direction, so I net is slowly increasing. Let's get to the bottom of it using Kirchhoff's rule. So tell me, what would be the potential difference between A and B? Let's go clockwise through this loop. If we go clockwise through the loop, who remembers going from A to B, what happens? From what? Ohm's law, it will be the potential difference between A and B has a magnitude I times R. Is it a drop or is it a rise? It's a drop because we are going in the direction of current. So this is going to be going from A to B, it's going to be minus I times R. This is the net current in the circuit. Does that make sense? I is the net current due to everything taken together, the battery's effect and the induced EMF's effect, both taken together. Okay, what about going from B to C? See, the thing is the induced EMF is opposing the battery, the EMF due to the battery, right? Isn't that true? So the induced EMF is not in the same direction as the battery EMF. So which way should it be? If this thing is trying to send current this way, shouldn't it be as though there is a positive generated at this end and negative generated at this end, so that the current I induced is flowing this way? Right? So if you go from here to here, from B to C, do you see that there is a drop? Because you're going from positive to negative. And in fact, you can see it from this negative sign that comes from Lenz's law. The fact is that V induced here should be negative. So V induced here, the induced EMF is minus L di over dt. There is this minus sign that says that the plus will be this side and negative will be this side, so that the induced current opposes the external current. So this is also minus L di dt. This is the V induced. When I go from here to here, there's a drop also. Right? Is everybody clear? Okay, what about here to here? Nothing. And here to here, there's a rise. I'm going from negative to positive. So this is going to be plus V battery. This is equal to 0. Okay, V battery is constant. This is a differential equation, right? It turns out this is a first order ordinary differential equation, which is really easy to solve. So anybody who has taken a differential equation course will realize, what are we solving for? The current. We know everything. We have been given what is the resistance in this circuit. We have been given what is the inductance of the coil. You know, maybe the inductance of this coil is, let's say, 5 Henry or something. So we have been given the inductance, we have been given the resistance, we have been given the battery voltage. What we need to find is the current as a function of time. So solve this differential equation for I, and what we will find is that the current at any given time turns out to be V battery divided by R, 1 minus e to the power minus t R over L. This is what it turns out to be. And by the way, you know, this thing R over L can be given a shorter name if you like. I can write it like this. I can say this is T divided by tau, where tau is equal to L divided by R. This is called the time constant of an LR circuit. Again, what should be the unit of this thing, L divided by R? It better be second. And I want you to take the time at home to make sure that the unit of inductance, which is Henry, and the unit of resistance, which is ohms. So Henry divided by ohm, I want you to go back to what those names meant, because those things mean something, right? Go back and make sure that Henry divided by ohm is literally seconds. You know, it better be 1 Henry divided by 1 ohm should be 1 second. So this is what it is. Now let's try to plot this thing. Do you see that here, if I know that this is what the current is, I can actually plot it out, and you will see in a minute that this is exactly this graph that I have shown you here. Let's make sure that it really is this graph. Okay, so let's try it. What will be the current at time t equal to 0? At time t equal to 0, what is e to the power 0? 1, right? And what is 1 minus 1? 0. So you can see that the current is indeed 0 at time t equal to 0, right? Okay, let's try another extreme case, t equal to infinity. If t is equal to infinity, what would be e to the power minus infinity? Tell me e to the power minus infinity, which is the same as 1 over e to the power infinity. What is e to the power infinity? Infinity. So this is really 0, right? So do you see that this term then goes to 0 very long time after, right? So that means t going to infinity, what you have here is that I becomes equal to V battery divided by R 1 minus 0. Why? Because this term here becomes 0, right? And therefore what you see is that I is equal to V battery divided by R. And this is exactly what we were saying. We were saying that the current will become equal to the maximum value, which is just V battery divided by R. The inductor becomes useless at that point. It doesn't do anything. So do you see what we are really trying to say? We are saying at time t equal to 0, this is the t equal to 0 time, the inductor, induces the B induced, which has exactly the same magnitude as battery voltage, right? So that there is no net current at time t equal to 0. So this starts opposing, as soon as you close the switch, this opposes the rise in current through it, because that will increase the magnetic flux through it so much that the V battery and V induced are exactly the same, so there's no current. But then slowly V induced keeps decreasing so that battery wins out, and there is a current, but not the maximum, and ultimately the inductor gives up. At that point, there is no more any change in flux. So all of this is happening while you are closing the switch. Is everybody convinced that this corresponds to that? Right? So what is what would be this time constant thing? You can see that is the time. If t became equal to tau, then what would be the current at that time? I will be equal to V battery divided by R 1 minus e to the power minus tau over tau. Tau and tau get cancelled, which means the current will become V battery over R 1 minus e to the power minus 1, which is nothing but 1 over e. So basically we have defined this thing called the time constant, which is L over R, which says how quickly the current will go to 1 minus 1 over e of its maximum value. It just says to you how quickly the current will go to the maximum value. Is that making sense? Okay, now can you tell me what will happen if I open the switch? Now let's talk about the case where the current has been going for some time and now I open the switch. What will happen when I open the switch? Anybody? Do you think the coil will again oppose changes? Yes, it will, because it got used to having a current through it. So basically when we had the switch closed for a long time, after a long time, do you see that this B induced went to 0? Because there was no di over dt, there was no change in current. So it went to 0. But now if I open the switch, will the coil again oppose the fact that you are actually decreasing the current? And this time it will try to maintain the battery current. Because when you open the switch, you're trying to remove the battery from the circuit. It's like not having the battery in the circuit, right? So this time, this coil will try to maintain the current. So which way should the induced EMF be? This time it's like you have a positive generated here and negative generated here, and this thing tries to replenish, the current that the battery was providing. So this time again the current will not suddenly drop to 0 as soon as you open the switch. Suppose this is the time, when you open the switch, you won't see the current go plop down all of a sudden. What you will see is that the current will actually exponentially decrease, and go to 0 over a period of time. Does that make sense? So let's try to, so this is the time, t open. T for opening the switch. So let's try to figure out the math for that. And again, it's not very hard. All you have to do is in this equation, for figuring out what happens. So I'm talking now about case 2, and this time we just opened the switch. Who wants to tell me how can I change this equation that we got from Kirchhoff's rules to correspond to that case? Should I just get rid of the battery? Yeah, let's just get rid of the battery. If you get rid of the battery, again, this is a differential equation that we can solve. If you solve this differential equation, this time you find the solution is this. It is This is equal to E t over tau. Tau is exactly the same as what we had found, this thing. This time, for the case where we open the switch, if t is equal to tau, then the current will be V battery divided by R e to the power tau over tau. I'm just trying to plug t is equal to tau here, and what you see is I get I is equal to V battery divided by R, and this is 1 e to the power minus 1, which is 1 over E. So again, the time constant tau is equal to L over R is defined as the time in which the current will go to 1 over E of its maximum value. Please.
If you got rid of the V battery, where does the V battery come from in the equation?
Which one? Oh, if you like, this is, you know, one way to say this, that's a good point. This V battery over R is really I max. If you like, I should call this thing I max. So this is I max, where I max is V battery divided by R. So basically what we are doing is we had actually, initially we had some maximum current in the circuit. See, remember we had closed the switch. Remember what we did? We closed the switch, right? And we kept it closed for a long time. After some time, this coil became useless because there was no di over dt, there was no di over tt. And so what happened to the current in the circuit? It became its maximum value. And that maximum value is going to be V battery divided by R. So if you like, you can just call it I max. But the I max in our circuit is really V battery divided by R, because initially we had made that current to be something due to that battery that we had connected. Is that making sense, folks? Any questions about this? Okay, so what will happen in this case? Let's again try to look at the two cases. This is not true this time. So what happens at t equal to 0? Who wants to tell me? T equal to 0? The current is I max, isn't it? I is equal to I max. What happens at t equal to infinity? If I put t equal to infinity, what will I get? Yeah, because you can see this will become I is equal to I max e to the power minus infinity, and e to the power minus infinity is 0, so this is really 0. So basically what we are saying is that the plot will look something like this. You would see a curve, let me redraw it, that looks like this. It has current as a function of time, which starts out with some maximum value, I max here, and then it exponentially decreases and goes to 0 after a very long time, right? After a time, just a second, after a time t is equal to tau, which is, you know, L divided by R, after this time, we are saying the current has become 1 over E of its maximum value. Please.
What is the time over tau? Like, what does that represent at what time?
No, tau is a very special time for this circuit. It's called, you know, the time constant. It's a characteristic time in the circuit, and that's the time after which what you will see. So if suppose we choose a time here, you know, let's say we choose t is equal to tau, you know, this is some time, then if we try to see how much is the current here at this time, what you would see is that the current here, if this current we are calling I max, this current for this time has become I max divided by E. You know, this is I max divided by E. Remember, because this is our I max. So basically the current has decreased by this factor E. Everybody is familiar with E, right? E, what is the value of E? Yeah, it's like 2.71 roughly. It's the exponential, right? So E is e to the power 1. So basically it's 2.71. And so the point is that the current at this time would have decreased by t is equal to tau corresponds to that time where the current would have decreased by a factor 2.71 of its maximum value. In fact, this plot is not showing that very well, so maybe I should choose it somewhere over here actually. So this is t is equal to tau is the time when the current has actually decreased by, you know, this is I max divided by E. E, remember, is 2.71, which is almost 3. So it's become I max divided by 3 roughly. It decreases by a factor of 3 compared to the maximum value. Any questions, folks? All right, then the next thing that we are going to talk about is how much is the energy that is stored in the inductor. Do you think an inductor will store energy? What kind of energy will inductor store? As opposed to a capacitor, which stores, what kind of energy can you store inside of a capacitor? Anybody remembers? Electrical energy, right? Because you have, in a capacitor, you have two metal plates that have opposite charges, and there is an electric field between them. So you have electrical energy stored there. Now in an inductor or a coil, if you pass current through it, because of this current, you have what inside it? Magnetic field, and so you have magnetic energy stored inside an inductor. Let's try to figure out how much is the magnetic energy if suppose some current I is passing through it, and of course how much is the magnetic energy will depend upon which property of the inductor you think. Can you make a guess? Should it depend upon L? Like in the case of capacitor, does anybody remember what was the total energy stored inside a capacitor which was being charged, let's say, with a battery which has a potential difference V, and the capacitance of the capacitor was C? Very good. It was 1/2 CV square. You know, based upon that, you can already guess how much would be the energy stored inside of an inductor, inside of this coil. This time it's going to be magnetic energy. Let's try to figure it out. So we are going to talk about the magnetic energy stored inside of an inductor. So let's say that this inductor has some current I flowing through it. Okay. One thing that you should remember from the previous class is, what can I write power as? Power means, this is power. Power is what? It's energy per unit time, right? And if there is some current flowing through something and there is some potential difference V across it, can I write the power as I times V? Can I say that this is the power output of an inductor if it has a current I flowing through it and if it has a potential difference V across it? Okay, what is the potential difference V across an inductor? Here, isn't this the potential difference across this inductor? L di dt. By the way, that minus sign just reminds you of Lenz's law. The minus sign just reminds you that inductor always tries to maintain a status quo. It does not want the current through it to increase or decrease. It wants it to remain constant, right? So that's what the minus sign means. I don't care about the minus sign. I'm only going to worry about the magnitude here, okay? So P, power, means du over dt. Is that right? This is the magnetic energy. U sub B is the magnetic energy. So I'm going to give it a name. Magnetic energy is U sub B. So power is du over dt, magnetic energy per unit time, and that should be equal to the current in the inductor times V. And V, we can see, is L di over dt if I don't worry about the sign. So I'm not going to worry about the sign because I'm not interested in the direction of induced current or things like that. I'm only interested in the magnitude. So from here you can see that I can write du as IL di. I just got rid of the dt. So I got rid of the dt from both sides and I have du sub V, infinitesimal change in the magnetic energy is equal to IL di. So what would be the total magnetic energy stored? Can I integrate both sides? Yeah. So total magnetic energy stored, let me do it here. Total magnetic energy, U sub B, can be found by integrating this. So U will be equal to integral dub, which will be equal to, okay, integral dub, which is this thing, I L di from, let's say, 0 current to some current I. So we are trying to figure out how much is the magnetic energy stored in this coil or solenoid or inductor if the current goes from 0 current to some current I. Is L constant? Can I pull it out of the integral? Yes, L is a constant that can be pulled out. What is x dx? Integral x dx? X square over 2. So that will be exactly integral I di will be I square over 2. So you can see this is L I square over 2. If I put the limit, the upper limit is I, it gives me I square. Lower limit is 0, it gives me 0. So this is the total energy stored in the inductor, right? If the current goes from 0 to some maximum current, I in this case. Does that remind you of the formula for the capacitor? It should, because for the capacitor, compare this. This is the use of B. Compare this with capacitor. Recall that use of E in the case of capacitor was half C V square. This is electrical energy stored in capacitor. So here, how much energy is stored depended on C. Here it depends upon L. Here it depends upon what was the voltage that you had applied. Here it depends upon how much is the total current. Any questions about this? Okay, if you remember, for the case of electrical energy stored in a capacitor, we had also found something called energy density. That means energy per unit volume. How much is the energy stored in 1 meter cubed of the capacitor, right? And what was that? Does anybody remember what was little use of E is the name we gave it, and this was the capital use of E divided by the volume. So this is how much is the energy stored per unit volume. That means how much is the energy stored per meter cubed of the space between the plates of the capacitor. Anybody remembers this? If you remember, this turns out to be half epsilon 0 times electric field square. Electric field is the electric field in a region between the plates of the capacitor. Do you remember half epsilon 0 E square? Can anybody make a guess what we should be able to find, what we should find here in the case of inductor? We are going to do it in a second, but make a guess, because you should be thinking about what we are doing. It's not about writing it down because it's all there in the book, but think about what it should be. I want to now figure out what should be the magnetic energy stored in this coil if I look at 1 meter cubed of this coil. If the current through it is I at some time, its inductance is L. Can you make a guess about what should be the magnetic energy stored inside this coil as the current I is passing through it? At least can you tell me what could it depend upon, which way? Go ahead, please.
The 1/2 mu sub 0 v squared.
Very good guess, because it will be very close to that. Mu sub 0, it will turn out will be in the denominator, but b square, very good. That's exactly what I wanted. I didn't care about the constant anyway, but the thing is, you're absolutely right. We will see in a second that now, if we try to figure out what is little use of B, this is energy per unit volume. This is the magnetic energy per unit volume inside of a coil or an inductor. This will be capital use of B divided by the volume. Okay, so capital use of B is this, half Li square. So this is half Li square. And again, to do this calculation more concretely, let's think of this coil as being a solenoid. All right, remember? And we are going to assume it's an infinite solenoid. Just for simplicity, let's make it infinite. So the thing is, if we have really long solenoid, the only, just make it very long. These are extremely long things. First of all, do you remember last time I already calculated for you the self-inductance L of a solenoid? If you recall from last class, I showed you this, that L was equal to mu 0 n square A times L. Do you remember this? In other words, what I showed you, that L only depends upon the geometrical properties of a coil, right? It depends upon how many number of turns per unit length it has, what is its area of cross section. In this case, if it's a circular coil, then pi r square, right? That will be the area of cross section. What is the length L? L is this length, L is this length. So it's not infinite, but it's almost infinite. L is very, very large. So unlike this formula, which can often confuse you, because I want you to understand that this formula does not say that L depends upon phi of B or I. Why? Because if you increase the current, the magnetic flux through the coil will increase such that this ratio will stay constant. For example, for a solenoid, the self-inductance is only dependent on the number of turns per unit length, area, and L. It's a geometrical property of the coil. Just like capacitance of a capacitor is a geometrical property of the capacitor. So what we are going to do, and remember, does anybody remember what was the magnetic field produced by a solenoid? Do you remember this was also, you learned in a few classes ago, this was mu 0 n times I. Using Ampere's law, do you remember we found an expression for the magnetic field inside of a solenoid to be mu 0 times n times I? Let's make use of that. If we make use of that, what we will see here is that we have half, instead of L, I'm going to write this. So let's write for L this thing, mu 0 n square A L times I square divided by volume. What is the volume of this coil, this solenoid? Tell me. If the solenoid has a length L, which is very, very large, and its area of cross section is A, what should it be? Should it be area times what? Area times area of cross section. Think about it. If I ask you what is the area of, what is the volume of this cylinder, because coil is like a cylinder, isn't it? If I ask you what is the volume of this cylinder, the volume of this cylinder is whatever is the area of cross section multiplied by the length, isn't it? That's the amount of space that it takes. That's the volume. Volume is the amount of space it takes. So divided by the area times the length. Notice that area gets cancelled with area, length gets cancelled with length. Hey, what are we left with there? Do you see that we are left with this thing, half mu 0 n square I square. Let's try to, I want to put it in a form where I can pull out this B, because your friend has already told us that it should depend upon B square, and you can already see the trend there, that it's looking like B square. What I can do is, can I multiply and divide by mu 0 always, and divide by the same thing? If I do this, do you see that this whole thing now is mu 0 square n square I square, and that is B square, isn't it? So what we have found is that this is equal to half B square divided by mu 0. This is the magnitude of magnetic field. So what you can see is, what we have figured out then is that use of B, that means energy per unit volume stored in the magnetic field inside of an inductor, is this. And again, just like we said in the case of capacitor, we said even though this formula is only derived for a particular case of a coil, what you will find is that this is a universal formula. In other words, the energy stored in a magnetic field per unit volume in any small region, if you have a magnetic field B, will be given by this. So later in the next chapter, we are going to talk about electromagnetic waves, and we are going to say, oh, light, for example, visible light is an electromagnetic wave that consists of electric field and magnetic field. And if we are going to think about how much is the energy stored in the magnetic field per unit volume, it will again be half B square divided by mu 0. Does that make sense? So this is a general formula even though we derived it for the case of solenoid. So by the way, so do you see that if I told you how much is the magnetic field inside this thing here, what is the B? Will you be able to tell me what is the magnetic energy per unit volume? What if I asked you for the unit of B square over mu 0? What should be the unit of B square over mu 0? Go ahead, please. Excellent. It should be joules per meter cube because you can see half does not have a unit and use of B depends upon B square over mu 0. So obviously the unit of use of B this is the same as unit of B square over mu 0, which should be energy, which is joules per unit volume. That means meter cubed, joules per meter cubed. Any questions, folks? Anybody? Okay, then the last topic from this chapter is going to be on mutual inductance. And this idea is really not new at all. What is this idea then? Here is the thing. If you have two coils, and I have actually mentioned it before, so it should be absolutely no problem for you at all. Think about it this way. If I have two coils, here is one coil and here is another coil. Both of these are right next to each other such that, you know, any magnetic field that is due to the current here is actually going through the other loop also. In this case, if I change the current through this coil, right, if I change the current through this coil, you are right, there will be an EMF induced in this coil due to the fact that we talked about this, due to the self-inductance of this coil opposes a change in current through it and it induces an EMF, V EMF is equal to minus L di dt, right? But would you also expect an EMF to be induced in the coil that is sitting next to it? Wouldn't you? Because the magnetic flux due to this coil is also looping through the other one. So if I change the magnetic flux here by changing the current in this, am I not changing the flux through that? Magnetic flux through that? So that coil is also going to oppose a change in flux through it, and there will be an induced EMF and induced current in the other coil also. Shouldn't it? And this phenomena by which two coils which are sitting next to each other can induce EMF and induce current in the other coil which is sitting next to them, because the flux through one coil is looping and passing through the other one, is called the phenomena of mutual inductance. So this is the phenomenon of mutual inductance. So let me write it down. It's not a very different thing from what we have been talking about. Here we talked about self-inductance, the coil inducing an EMF in itself because it sees a change in current through it. In the other case, you're changing the current in one coil. So it's now there's another coil sitting next to it. It sees a change in the flux through it because it's the flux through one coil is looping through the other one, and hence there is an induced EMF in the other one. So this phenomena of mutual inductance just is this idea that if you have two coils next to each other, suppose you put an ammeter here and you connect this to a battery. So this is coil 1, this is coil 2, they are both next to each other. This is your switch here. As soon as you close the switch, this is your V battery. As soon as you close the switch, is everybody agreeing that due to self-inductance, this coil will oppose, there will be an induced EMF, V induced, which will be minus L di over dt across this coil that will try to oppose the increase in the current. So the current will slowly increase to the maximum value as we discussed, as opposed to going to maximum value all of a sudden. But what do you expect here? Will you expect anything here? Yes. Will that coil also see? Because the magnetic flux due to the current is actually passing through both. Isn't it? Because they are sitting next to each other. Just think about it, Right now the current is 0 in both coils. Now let me show you what will happen, and let me just show you this demo here. So watch what happens. What I'm going to do is I am going to close this switch. And this switch, by the way, this battery here is connected only to one of the coils. This coil here is connected to this ammeter. which you are seeing there, watch what happens when I shut the switch. Look there. Do you see there is an induced current somehow in the other coil also for that short period of time that I made the change? Now the coil got used to it, both coils got used to it. Let me open the switch. Do you see again when I open the switch, again this coil is not the only one that has induced EMF and induced current in it, which is saying no, I want to replenish the current that the battery current that you're getting rid of. Even this coil opposes a change in flux through it because it is sitting right next to the first coil, and so the magnetic flux, these magnetic field lines are due to the current in this circuit, right? But they are looping through the other one as well, and hence there is an induced current here. And this phenomena by which you induce a current in the other coil is called the phenomenon of mutual inductance. Similarly, what do you think will happen if I change, if I keep again, I close the switch, if I change the resistance in this coil? You know, this is a device called rheostat which can be used to increase or decrease the resistance. If I increase the resistance in the first coil, which is connected to the battery right now, do you think that will change the current in this coil? It will, right? Will that do anything to the other coil which is not connected to any battery? Nothing? Just connected to this ammeter that shows whether there's a current or not? Would you expect anything? Yes, because if you're changing the resistance in the first coil, watch what happens. So again, for the period of time that I make a change in the current in the first coil, I see that the other coil also has an induced EMF and induced current because the magnetic flux due to the current in one coil is looping through the other one. This phenomenon is mutual inductance. Does that make sense? We can now define some quantity called mutual inductance of two coil system, and we are going to give it a name M. This thing called M is very much like that quantity called L, which is the self-inductance of a coil, which is just for one coil. So the coil has an induced EMF in itself when you change the current through it, and that will depend upon this thing called L. But when there's another coil sitting next to it and you are inducing an EMF in that, that will be due to this property called M, which depends upon the geometry of both coils. And we can write this, that induced EMF in coil 2 will be equal to what? Can somebody tell me what it should be equal to? Minus some constant times di1 over dt. What should be that constant, folks? Just try to compare it with this one. V induced in the same coil is minus L di over dt. V induced in the other coil due to the flux that is looping through the other coil because of the change in current in this coil would be? Can you think of what the constant should be here? This is this constant, the mutual inductance of the two coils taken together. And again, M will depend upon, this is a constant called mutual inductance of the two coil system. It will only depend upon the geometry of the coil. It will depend upon N1 and N2. We are not going to derive those expressions for M, but it will depend upon N1, N2, A1, A2, etc. You see what I'm saying? L1, L2, etc. By the way, if I had reversed this whole situation and suppose I was actually, you know, I removed the battery from here, right? And I actually connected the battery here. And suppose I put an ammeter here. Again, will the same kind of thing happen if I close the switch here or open the switch here? Will there be an induced current and induced EMF here? Yeah, so this is like a symbiosis, you know, it's a mutual relationship. So I can also say this, V induced in the first coil can be written as minus M di2 over dt. So if the current in this coil is changing, it will induce an EMF in this coil, right? Any questions about this? Okay, this is all you need to know in the chapter that we were in right now. We are going to later come back to mutual inductance in the next chapter and try to look at its application for transformers. Remember we talked about transformers? Or do you want to talk about transformers now? let's actually do it, because I think the book has actually placed it in a very strange location. I think in the book, this particular thing is at the end of the next chapter, all right? But let me just talk about it here, because it's a very nice application of this fact that if two coils are sitting next to each other, and the flux, and you are changing the flux through one coil, and it's also looping through the other one, you are inducing an EMF in the other one. You know, this phenomena of mutual inductance, this particular thing. And do you see that this is due to Faraday's law? We are really talking Faraday's law, right? This particular thing is really useful for making transformers. Remember transformers I had come back to earlier also? What do you remember about transformers? Anybody? What are transformers for? Because I had explained it to you, and in fact I even told you that transformers are so useful for our lives that you cannot imagine lives without transformers, because of in fact it's mainly due to transformers that we have a current in the coil in our house that is actually alternating current. You know, the current that changes direction, you know, 50 or 60 times, you know, it switches direction. So it could be 50 hertz or 60 hertz could be the frequency of how many, you know, the current going one way or the other. Can anybody say what transformers do? Because this is so important, you know, you cannot leave this class without knowing what transformers are. So tell me what they are. What do they do? Why are they so important? I told you several applications, and let's start thinking about them one by one, please.
They transform alternating current into direct current so that it can...
No, that would be a diode. You know what? You know that would be a diode. But what transformers do is they actually transform the voltage, the potential difference from one value to the other. Because what we said is that in many applications, you might want to have your hair dryer working at 3 volts. On the other hand, the power supply in your house is giving you 120 volt. How do you convert 120 volt into 3 volt? Transformers will do it for you. Similarly, your electron tube in your TV requires thousands of volts. How do you convert 120 volt to thousands of volts? Your transformers will do it. Not only this, in fact, I even told you earlier that when the electricity is coming from, say, Chicago or some faraway area to Pittsburgh, because maybe we don't make electricity in Pittsburgh itself, the power companies are over there. What do you think, you know, do you think we are losing a lot of energy in the form of heat? Yes, we are. In fact, it turns out that if you lose only 1/4, you are doing a good job. So why is that? Because in the power lines, in the houses, you lose because of I square times R. You might say, oh, but those copper wires, don't they have a very small resistance? Why would I lose so much energy? Well, it turns out that those wires are so long. Remember, resistance R is equal to rho resistivity times L divided by A. This L is so large coming from Chicago to Pittsburgh, that those lengths, that even a small resistivity will cause a huge resistance, right? So we could lose a lot of power. Now we have to be careful. We have to think about, oh, if power depends upon I square times R, you know, is there a way to minimize the power loss? And the thing is, you can again minimize the power loss by sending energy from the power company to our house at high voltages and low currents. Let's see why. So suppose you want to send a certain amount of energy per second or certain amount of power to Pittsburgh, and let's say that the need for the city, I don't know what the need is really, I'm going to just make up, and maybe this is a ridiculous number, but I'm just going to make up something. Let's say that, you know, the power company was trying to send power which was, say, 500 megawatts, you know. So we are now talking about transformers. And their job is to change the output voltage compared to the input voltage. And one use is in minimizing the power loss in the form of heat What I mean by that is this P lost in the form of heat is I square times R. So minimizing this power loss in the power lines when the power is being sent to our house. Okay, so the thing is, let's say that I'm not going to say Pittsburgh because maybe this is a very strange number for Pittsburgh, but let's say that the power company is trying to send 500 megawatts of power. Does anybody know what's our power needs in Pittsburgh here for about 500,000 people? No? I don't know either. So let's say that the power needed is 500 megawatts. That means 500 watt, 500 times 10 power 6 watts. Right? Are there many ways, and do you remember this, that power, I hope that everybody remembers that power is current times the voltage, right? Can power be written as current times voltage? Okay, now do you see that there are many ways of sending this power? Because you can increase your current, then you will have to decrease your voltage such that I times V stays 500 megawatts. Isn't that true? Let's try two things. Let's try two numbers. So what do you want current to be? So case 1, we are engineers trying to decide what should be the current or what should be the voltage that we should be using to send power. Case 1, what should be the current? Can you choose one current value? Let's say 500 amperes. Okay, if 500 amperes is the current, what have we already determined for the voltage? Tell me. We have already set if the current that we are going to use will be 500 amps, the voltage should be what to make the power this? Shouldn't it be 10 to the power 6 volts? Such that this times this is this number. Let's see how much is the power lost in the power line. The power lost will be I square times R. And let's say that the resistance of the coil is 100 ohms. How about 100 ohms? Any suggestions from you guys? 100 ohms, is that sounding good? I hope that we don't lose everything. Before the power reaches our house, it's all gone in the form of heat. That could happen too if you choose the resistance to be very high. So what is the power lost? Isn't this I1 square times R? The R is the resistance of the copper wire in those power lines all the way between Chicago to Pittsburgh. That's R. All right. So I1 square times R will be 500 amperes square times 100 ohms, which is equal to how much? 25 times 10 to the power 6, isn't it? Is that correct? Okay, so actually we didn't lose that much, so this is not as bad. But but you can immediately see that if suppose this number was not 100, suppose we had chosen 500. Let's increase this thing. Now I'm getting a little bit more bold after looking at these numbers. So let's try to be close to the right number. So if this was 5, what would it be? 5 times this, so this will become 125, wouldn't it? Can you tell me how much is the power actually delivered to Pittsburgh? This should be equal to whatever was the being sent. This is the amount that is being sent. Let's say this is the amount that is being sent. It will be whatever was the sent amount and whatever is got minus whatever got lost. Isn't that true? So what we have here is 500 megawatts minus 125 megawatts. This is also 125 megawatts. And so this is equal to 375 megawatts. Actually, we have done better than most power companies do. We have been able to save a lot of power here. But let's try and see what happens if we actually crank up the current. Let's say we make the current 1,000. Let's try case 2. So case 2 is, let's say the current was, let's say 2,000 amps. Who wants to tell me what should be the voltage at which it should be sent? What should be the potential difference at which it should be sent if the power that was being sent is 500 megawatts? Huh? Do you see V2 should be power sent divided by I2, which should be, 500 megawatts divided by I2, which is 2000 amps. And so this should be, you can see, 250 times 10 cubed volts. Isn't it? Is that correct? 250 times 10 cube volts. Okay, great. So if that's the thing, how much is the power lost? Is it I2 square times R? It's the same resistance. The coil resistance has not changed. It's the same resistance, 500 ohms. Let's see how much is the power that is lost. It's 2000 amps. This time, if we are sending it at 2000 amps, it's this square times the same exact resistance of the coil in the power line. How much is it? 10 power 6. Okay, so this many watts. In fact, do we even have this many watts? No. So in fact, even before the power arrives, everything is gone. Do you see that this thing is more than what we were wanting to send? Right? So this is absolutely ridiculous. This thing, in fact, will not happen. Let's say we made it 1000. If we made it 1000 here, I hope that everybody understands that point. Everything is lost, even before arriving, gone in heat. Nothing is left, right? So this thing you cannot do. But let's say that this was this was, let's say, 1000. Let's make it 1000 amps. If that is 1000 amps, let's make this 1000. In this case, this thing is 500 times 10 cube volts. In this case, what will be I square times R? This will be 1000 square times 500. 500 times 10 power 6 watts. What is the power actually delivered? Somebody from the first row, what is the power actually delivered? What is it? 0. Because the thing is, each of them is 500 megawatts minus 500 megawatts, which is 0. So you can see that all you have done is you have tried to send the same amount of power, but as you decide to send higher and higher current and at lower and lower voltage, what happens? More and more of it gets lost in the form of heat. Less and less actually gets sent to the house. So what is the moral of the story? That you should try to send power from the powerhouse to your house at what? Right, at high voltages and low currents. If you send it at high voltage, first case is better. That was high voltage, V1 was greater than V2, right? Higher voltage and lower current is better because in this case you are losing less in the form of heat in the wires. Is everybody understanding that? Of course, there are limitations. You cannot make the current extremely low in these wires and the voltage extremely high in these wires. That you cannot do that. So of course there are some limitations, technical limitations, but does everybody appreciate you should try to make it as low of a current as possible within your constraints in order to minimize the power losses. And I told you already, if 1/4 of power is lost, power companies consider it to be great achievement. On the other hand, when the power comes to our house, and I have 2 kids, they're 10 and 12, do I want them? And I know that they keep putting their hand, in fact, they're trying all sorts of stunts that really worries me. They're putting everything that they find with pokes, like they're trying to put it in the sockets and things. They could really get hurt if the voltage that the power company was giving to us was as high as, say, 10 power 6 volts. So somehow we want the voltage in our houses to be not, megawatts, but we want it to be, okay, 120 volts sounds like a reasonable thing, right? So somehow the power company needs to send power at a high voltage in order to minimize these power losses, but then when it gets to our house, it needs to be at a reasonable voltage so that it's not dangerous for us. How do we do it? How do we decrease the voltage right before it arrives in our house? We can use a transformer again. Do you see? So you want to send the power at a high voltage to minimize the losses, but then you want to keep it at a lower voltage in your house, like 120 volts, to make sure that it's not dangerous. If by mistake something gets, we touch something, it's not, and if there is a circuit, complete circuit, we don't get hurt by it. So we want to be able to reduce the voltage as we want. What will do it? Transformers. In fact, if you've taken any trip to, for example, outside of the city, and most of you have you seen those huge transformers, along the roads right outside of the city? Those are the transformers that are trying to do that. They're trying to actually reduce the voltage right before it gets to our houses. Does that make sense? So let's now talk about the principle of transformer. So let me show you the construction of a transformer. And basically the transformer consists of two coils. So one coil is called the primary coil or input coil, and the other coil here is called the secondary coil or the output coil. Okay? This primary coil is basically what's connected to your, this is the input, for example, in your house. This is your 120 volt, and when I write this as a squiggle like this, this is maybe my alternating current power supply. Maybe this is my 120 volt, power supply. So the voltage here in the primary, let's say, is V sub P. This is the name that we are going to give. Now what we are going to do is we are going to use iron core to make sure that as much as possible the magnetic flux that is passing through the primary coil, if I close the switch here, let's say we close the switch here, think about it this way, this is the input, right, of the primary. As soon as I close the switch, this is my power supply in my house. I'm talking about, and suppose this was my hair dryer. Here I had my output is, let's say, my hair dryer or my TV or something like this. So this is some load or resistance, this is the output, and maybe it's a hair dryer, maybe it's a whatever you want to call it, and let's say that the voltage across it is V sub S, which is the voltage in the secondary. Now here is the thing, why is it that I am going to use an iron core to connect the two? What is the advantage of an iron core? Because do you see that as soon as I close the switch, and this thing is a 120 volt power supply, and this is an alternating current, sometimes the current is flowing this way, sometimes the current is flowing this way, sometimes the current is flowing this way, sometimes it's flowing the other way. Do you see that the magnetic flux through this, magnetic field lines here, are sometimes this way, sometimes they're pointing up, sometimes they're pointing down, sometimes they're pointing up, right? And if it's a 60 hertz power supply, like that many times the thing is actually going through one cycle. Do you see that? So would you call that a changing magnetic flux through this coil or not? Yes, the magnetic flux through this coil is changing. Now if suppose this coil was connected through this iron core to the secondary coil, we can assume, to a good approximation, again it's an approximation, it's not really perfect, iron is a magnetic material. You know that, right? Because iron gets, if you bring a magnet close to an iron gets stuck to it. So iron is a magnetic material, and in a magnetic field it gets magnetized and its spins line up, so it starts behaving like a magnet. So what it does is it channels these magnetic field lines, through this iron, we can channel the magnetic field lines through this iron core into the secondary coil. And our assumption is going to be that as the magnetic flux through this is changing, all these magnetic field lines are also going through the secondary as channeled by the iron core. And when there is a change in magnetic flux here, because magnetic field lines are sometimes up, sometimes down, here also they're sometimes up, sometimes, and sometimes up, sometimes down. So there is a change in magnetic flux here as well, just like here, due to this phenomenon of mutual inductance. This coil is next to this, and the magnetic field lines that are passing through this are also passing through this. And we are going to assume that all of the magnetic field lines in the primary are going to go through the secondary, because we have really channeled it very well through this iron core. This is an assumption. Of course, in reality, there's going to be less field lines through the secondary. We are not going to worry about those things here. Any questions? So let's then write down what can we write mathematically about the can I say this, that V primary should be equal to, let's say that there are n number of turns in the primary. N's of P is the number of turns in the primary, and n's of S is the number of turns in the secondary. You know how many windings there are? Okay, then if suppose from Faraday's law the induced EMF in the primary should be what? Who wants to tell me? Minus, should it be n d phi dt? Right, so minus n's of P d phi over dt. Similarly, since all these magnetic field lines are looping through the secondary, who wants to tell me what should be an expression for the EMF induced in the secondary? Go ahead. Should be minus number of turns in the secondary times, yeah, rate of change of flux. And we are assuming that all of the flux through primary is going through secondary as channeled by this iron core. So we are going to assume that this d phi over dt is the same. The rate of change of flux in the primary and secondary is going to be the same because there's perfect flux looping from the primary to secondary. Okay, looking at this expression, do you see that this first expression means that Vp over Np is equal to minus d phi over dt, and looking at this expression we can see Vs over Ns is equal to minus d phi over dt. And so long as these things are exactly identical, is it okay to say that Vp over Np should be equal to Vs over Ns? Shouldn't it? And that equation is the most important equation for transformer. This is called the transformer equation. Or another way to write this is Vp over Vs is equal to Np over Ns. This thing is called transformer equation. Okay, notice one thing. So what we are saying, can you guys see it? No? Can you see it?
Yeah.
Okay. So the thing is, one thing that you can see from here is if Np is more than Ns, is Vp more than Vs? Isn't it? If Np is more than Ns, then Vp is more than Vs. So if suppose I knew that my power supply has 120 volts coming in, right? And I wanted to use it for my hair dryer that only needs 3 volts, should I be using more turns in the secondary or less turns? Huh? I have to make a transformer like this, right? And in fact, it's already built into your hair dryer. Inside your hair dryer is already a transformer that has 2 coils like this that will do it. But what do you think? Should the secondary have less coils? Yes. We want the voltage to decrease, so in that case the secondary should have less coils. As you can see in this case, let's try it. Suppose if we wanted the voltage, so in this example, suppose the primary voltage was 120 volts and the secondary we wanted it to be 3 volts, and suppose we knew that number of turns of the primary are 1000 turns and we have to figure out what's n's of S. Do you see from here that n's of S, if I pull this here, will be n's of S will be Np Vs divided by Vp. This will be Np Vs divided by Vp, just using the transformer equation. And so we can figure this out. This will be 1000 times 3 volts divided by 120 volts, and that means 25 turns. We just need 25 turns in the secondary. So if you're making a transformer for your hair dryer, you should have a transformer like this. You know, this is the iron core. You have, you know, this is your primary input thing. Here you have 1000 turns, and here you have secondary. this has number of turns which is only 25, and this is your hair dryer. Right? Is that making sense? Any questions about this? By the way, the transformer that actually decreases the output voltage is called a step down transformer. So a step down transformer is the one in which output voltage is less than input. That means there are less number of turns here than here. On the other hand, if suppose there is a transformer used in your electron gun in your TV, and that's also built into your TV, that is trying to increase the voltage to thousands of volts from the 120 volt that's coming from your power line. In that case, should the transformer have more number of turns in the secondary, the output side? Yeah. That kind of a transformer will be called a step up transformer because it steps up the voltage. Is that making sense, folks? Any questions about that? Now here is another thing. Although the transformer is able to increase or decrease the voltage, do you think it will be able to change the power, increase the power in the circuit? Somehow in the output side compared to the input side? No, remember, never get fooled. You cannot create energy. So if there's certain amount of energy coming per second from the primary, at the best, and we are going to here assume that there's no power loss or anything, if you ignore all the power losses in the coils and windings of the transformer itself, then the power in the secondary should be equal to the power in the primary, right? That would be the ideal case. So in ideal case, which is what we are going to assume, power in the primary should be equal to power in the secondary, and this is the case we will consider all the time. That means the current in the primary times the voltage in the primary should be equal to the current in the secondary times voltage in the secondary, right? Because isn't this power I times V? Isn't that the power I times V? Okay, so what this will say to you, then look at this. This is IP divided by IS is equal to Vs divided by Vp. One thing that you can see from here is that the transformer that actually increases the voltage, that means Vs is more than Vp, Ip should be less than Is. Sorry, let me say it one more time. If Vs is more than Vp, Ip is more than Is. So if Vs is greater than Vp, that means that Ip is greater than Is, right? But the transformer, I don't want you to get confused. So that means transformers that are step up transformers will increase the voltage, but in the output, but the output current will be lower because the current times voltage will be fixed. That's what we are saying. So in this kind of a transformer, we are saying we reduce the voltage to, what was the Vs here? 3 volts. But do you think that the current here should be more than the current here? Shouldn't it? Yeah, because the thing is, so if this voltage is more than this voltage, here voltage is more than this voltage here, then the current here should be less than the current here. That's what we are seeing in this. Any questions about that? So if you are given, say for example, the current in the primary, you ought to be able to find the current in the secondary if you are also given Vs and Vp, using the fact that the power is constant in the input and output coils. The total power, the total input power and output power are constants. Is that making sense? Any questions? All right, then at this point, we are actually done with all the applications of Faraday's law that we wanted to talk about. I want to now move on to talking about a circuit. Remember I said we'll slowly build things in. So we talked about circuits just with resistors, just with capacitors, then with resistors and capacitors, then we talked about circuits which had L and R, inductors and resistors. Now let's talk about circuits that have just L, inductor and capacitors. And the last thing we'll do, the grand finale of this circuit business, will be when we'll put L, R and C, all three things. Because in your electronic circuit, any chip that you look at, it'll have all these three components, L, R and C. Let's try and see what happens in a circuit in which you just have inductor and a capacitor. What do you think will happen in this case? Does anybody have any guess for what we should see in this case? It's a really interesting circuit. Let me show you an experiment first to just prove to you that this is exactly what will happen. This circuit is a circuit which will show alternating current. That means the current will change direction. You have never seen a circuit like this before. All of the circuits that you have seen have had currents flowing in the same direction all the time. Let's see. Here I'm going to show you the actual demonstration and then we'll explain the physics behind it. So that is an ammeter. Right now what I'm going to do is I'm going to actually charge a capacitor. This is a capacitor, this is an inductor, this is a coil. All right? These are the two things in the circuit. Right now I've charged the capacitor completely. At this point I'm going to remove the battery from the circuit, and so that your circuit will just consist of a capacitor and an inductor. That's what this circuit is going to be as soon as I remove the battery from the circuit. Watch what happens now. Do you see the current is changing direction? That's why you see the ammeter going from one extreme to the other. Of course, in this case, the motion gets damped out in the sense that you don't see this thing happening forever. You saw that the amplitude of this oscillation kept decreasing. That means the current in the circuit kept decreasing, and finally the current was gone. Why do you think that will happen? In the theoretical case I'm going to talk about right now, this is not what we'll see. What we'll see is that the thing will keep going forever. This oscillation will keep going forever. What is there in that circuit that is not there in my model here? Go. Resistance. It's the resistance that's actually going to decrease the current in that circuit, because the resistance will lead to power dissipation, right? I square times R, and that means electrical energy is going out of the system in the form of heat, and soon you will see that it will get damped out. It's like a simple pendulum. In the case of a simple pendulum, in the extreme case where you could ignore all the damping effect like friction and air resistance, wouldn't you expect a pendulum to keep going back and forth forever? But in real life there's always going to be damping, because you cannot get rid of friction and air resistance, and if you can't, you will see that the amplitude of this motion will decrease and go to zero. In fact, there is an exact one-to-one analogy between a simple harmonic motion, say of a mass spring. Again, if I pull a mass is attached to a spring, I pull it, let go, it will oscillate, right? If there was no friction or air resistance, this thing will keep oscillating forever. But in real life there's going to be friction and air resistance, because of which that will slow down, right? There will be a one-to-one analogy between that case and our system here. Right now we are going to ignore damping, so forget about resistance. I'm not going to worry about it. Let me show you why there will be this oscillation, why the current is changing with time here. Let's think about it, and then we are going to do math after that. So we'll mathematically also see the same thing, but I want you to first conceptually see, yes, it makes perfect sense to me, and then math we can figure out easily. So let's start from some point. Here we started from a point where the capacitor was completely charged. So let's start with this point. If the capacitor is completely charged, and that's the moment when you shut the switch, which I did, do you see that all of the energy of the system is stored in the electrical energy of the capacitor? So in an LC system, oh, beautiful. This is exactly what I needed. This is the formula that I needed. So we are talking about LC circuits. And look, isn't this the energy stored in the capacitor? Right, half CV square. In fact, we don't need this right now. So just this, half CV square is the energy stored in the capacitor. Let's say that I had used, who knows, 10-volt battery or something to charge this. And if I know the capacitance of the capacitor, I can tell you how much is the electrical energy stored. I'll just multiply half C with V square and I'll figure out how much is the total energy stored here between the two plates, right? At this moment, I close the switch. As soon as I close the switch, what do you think will happen here? There's no battery anymore. What do you think will happen? Any thoughts, folks? As soon as I close the switch there, all you have is this inductor and this capacitor. Forget about the resistance in the circuit. We are going to ignore it for now. Can you tell me what should happen in this circuit? Should there be a current? Yeah, the capacitor in this case starts behaving like a battery and it's going to pass current. Which way should the current be flowing? See, what's happening is the electrons here now see, oh, there is a wire like this, you know, and wires has free electrons. So these electrons actually hate each other. They want to be closer to the positive charges, which they like. So the electrons start moving from this to this. And then our language is, we say that a current is flowing from positive to negative because of this flow of electron. Isn't that true? So basically what's happening is these electrons are going and combining with the positive charges, and that is what's giving rise to the current. That's what we say. And we use the language, we say the capacitor is discharging and giving out this current, because do you see that the charge in the capacitor will decrease as the negative charges go and combine with the positive charges, and you see a current flowing, right? So starting from zero current, you will start seeing a current in this direction. Now, as soon as the current starts to flow, you know, as soon as you close the switch, the current flows because of this capacitor now. Will the inductor like it? No. Inductor likes to maintain a status quo in terms of how much magnetic flux is passing through it, right? So as soon as this, in this case it's not a battery, it's a capacitor which is completely charged, which is also acting like a battery. In this case, as soon as you close the switch, you can see that the inductor starts opposing the fact that there is a current flowing through it, and hence a magnetic field associated with that current. So what will the inductor do? It will induce a current through it that is passing in the opposite direction, so that for a minute, you know, remember that anyway, I had shown to you that at time t equal to 0, the current stays 0 because the induced EMF here, which is minus L di over dt, will completely oppose this, you know, whatever this thing is trying to do. So at time t equal to 0, the current stays 0 because of the opposition of the inductor. But then slowly, remember I had drawn a figure like this, the current as a function of time, it was only slowly increasing, and at time t equal to 0, it was 0. Okay, but now as time passes, does the inductor get used to the fact that the capacitor is trying to send a current through it? That means the electrons are going and combining with the positive charges. So then you can see that the current in the circuit keeps increasing, and so you will see that the current is increasing. As the current starts flowing, is there an energy stored in the magnetic field inside of the inductor? Yeah, we learned that it's half what? L I square. Remember we learned today that the energy stored in the inductor will be half L I square. So as soon as the current starts flowing here, there is energy stored in the magnetic field inside of this coil or inductor, and that magnetic field U sub B is half Li square at any given time. Here it was 0 because there was no current, and hence there was no magnetic flux. So there was no magnetic energy stored here. So initially all of the energy is electrical energy, U sub E, which is half CV square. Then some of this electrical energy gets converted to mechanical energy. Now electrical energy is less. Why is the electrical energy less now? Because do you see that now there is less potential difference across the capacitor as more and more electrons go and combine with positive charges? Right? Okay. What happens after a certain time? Do you see all the electrons will go and combine with the positive charges? There is no net charge left here. Is everybody agreeing that there will be a time when all of the electrons from the negative plate have gotten and combined with the positive charges? In other words, the current has become maximum. At that point, the inductor has gotten used to having this current flowing through it. But now, hey, is the capacitor completely discharged? Isn't it? So capacitor cannot send any current out. Its electrical energy has gone to 0. But now the energy stored in the inductor has increased and become the maximum value. So in other words, whatever was the half CV square initially has now become half Li square. Do you see what I'm saying? So initially you have UE is equal to half C V max square. This is the battery voltage that you use to charge the thing, right? And what we find is that when I goes to I max, you know, so at this point use of B was what? Who wants to tell me what is use of B? When this thing is maximum, this is 0, right? This is this point here. All the energy is in electrical energy, nothing in magnetic. When I becomes I max, UE becomes what? 0, and UB becomes half L I max square. Isn't that true? And if that's what keeps happening, if the inductor tries to maintain this current, do you see what will happen as a result of it? So this time the inductor is inducing an EMF across it, and it is trying to keep this current going. I hope that everybody can see that if this current keeps going for a while, what does it mean? That means are more electron going in this direction? If the current continues to flow this way, aren't the electrons going this way? If the electrons are going that way, is this plate now getting positively charged? Because more electrons are leaving, hey, and those electrons are going there. And after some time what will happen, look here what's happened. This plate has gotten completely charged to the initial value here, but notice the polarity. Now the bottom plate is positively charged, the top plate is negatively charged. Here the top plate was positively charged and the bottom plate was negatively charged. But again at this point, you know what happens to the inductor? It was opposing, and at this point it gives up. It says, okay, fine, I'm used to it now. But that's the moment that the capacitor has now gotten fully charged, and it says, no, I can do something about it. You know, I can keep the current going. And this time the inductor gives up and it says, okay, I'm used to having no current through me. I'm going to stop resistance. But look what happens. This time will the capacitor start sending current? Yes. And which way the current will be? The electrons at this point will start to go like this and combine with the positive. That means the current will start flowing like this from the positive to negative. Do you see this arrow is showing you the current? So the current in some sense up to this point, notice which way the current was. The current was flowing counterclockwise here all the way till here in half the cycle, but now what has happened is the current is flowing clockwise. At this point, will the inductor again start to oppose? Yes. So the point is that basically the capacitor starts to discharge. Here the capacitor is completely discharged, but the inductor and the current, it says, okay, now the current can go to 0. I cannot do anything, but the inductor wants to maintain it. Inductor wants to maintain it. It wants to keep the current going like this, and if it wants to maintain the current like that, do you see what will happen as a result? Negatives. What will happen if the current is continuing to go like this because the inductor tries to maintain a status quo by inducing an EMF across it? That means the electrons continue to leave this plate and start to move to this plate. And if the electrons are moving from that plate to this plate, here we are getting positive, here we are getting negative. And then finally we are back to the square one, and this cycle continues. So do you see half the cycle the current was counterclockwise, half the cycle it's clockwise. Within one cycle, how many times has the capacitor gotten fully charged? It was fully charged at the beginning and it was fully charged here. Twice in one cycle the capacitor is fully charged, but one time its polarity is one way, the other time its polarity is the other way. Does that make sense? Let me do a very quick question. We have one more minute. I wanted to show one problem here, and it's very easy. Suppose I wanted to ask you, suppose I told you this. I say, tell me what is I max. In an example, I say, what is I max given that V max is 60 volts, the inductance is 3 Henry, and the capacitance is 1 farad. Do you think you can figure this out? If I ask you what is the maximum current in this circuit here, can you equate these two things? You can. You can say that when the current is, what you will do here is this. You will say, I know that half L I max square should be equal to half C V max square. Wouldn't you say that? Is this making sense? Because at one moment in this circuit, when the current is maximum, all of the energy is in the magnetic energy and it's half L I max square. At this moment, all of the energy is in the electrical energy and it's half C V max square. And so you can equate the two, solve for I max, right? Is that making sense? Is there any question? All right, folks, have a wonderful weekend.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.